minus I integral dt prime ti tf p squared prime over 2n plus bx n prime, and then minus this p prime x dot prime, like so. And if you really wanted to be careful, you would say that the t here is less than tf and bigger than ti. And you integrate all possible momenta at every instant. But please don't go all the way to the instant ti. Same with this. You could say t is less than x and tf and greater than ti. You could say that here too, because the x's that we're integrating don't include this last instant. You're being fussy. But I could just make it equal as long as I include a kind of a dumb boundary. Of course, you can make it equal if you put a delta function saying the last instant, don't integrate, just make it exactly. So we can do that by just putting something that says xi, so x tf equals xf, and x x at t so it's kind of like limits of integration. Okay, but in a slightly different sense. We're actually integrating x going from minus infinity to infinity. It's just that the last integral we're not doing. But it's convenient to write it like this. Why? Because if you just stare at this, it's just saying, here is time, here is xf and time tf, and here's time ti, and here's some xi. And what it's saying is, please draw all paths that start and end on these places. X is a function of t. And for each of them, you get some contribution and add them all up. So it's nice to include these final points, even though they're pinned, just because the picture tells you, you can remember the picture so easily. Just sum these paths. The p's, apparently you have to sum p's regardless. There's no instruction about the final p because it doesn't exist. You have only intermediate times and not the actual final. In fact, damn it, okay, so here, I'll do the last line and then we can, as I said, revisit the worries you might have next time. So we're going to do the integral dpt. Okay. There's a product over all times of integrals like this. Remember, this capital curly D is an n-fold or n over 2-fold p integral. And the typical p integral looks like this. Okay? The thing to notice about the p integrals is that each time the p integral appears in just one exponential in a very simple way. It's just quadratic in this p. I mean, up to quadratic order in this p. In fact, this thing, we can just complete the square of p and write this as p as 1 over 2m p squared t p of t prime, and then minus x dot t prime. And so I want to write this as something squared. But I need to get, I want to get this as the cross term. So that's, did I do it right?
No 2.
No 2. Thank you. Good. Okay. Yes. P. Oh, very good. And then I have the V again. But then I've got too many of this squared, and so that's plus a half m x dot squared. Right? Minus. Now here's the thing. This I can just call P tilde T prime. It's like somebody wrote P3 or Pi minus some constant independent of Pi. So it does depend on I. And said that squared, and I'm integrating over P1, P2, P3. Well, I would just call this P tilde I. Okay, I'm changing variables. But if I do that, then this thing, so I should just say, this thing is equal to integral dp tilde, integral dx again, e to the minus I integral dt prime, and let me write it like this, half m x dot squared t prime minus v of x t prime, and e to the minus I integral dt prime p tilde t prime squared over 2m. Okay. So what you can see is that the integral over p tilde completely factorizes from the integral over v. Okay? So that you can imagine just doing this integral. You get some answer. And the answer is proportional to, so I'm going to have to let you go, so I'll just say S. This is the classical action of X. So here is the classical action. You see, if I drop the P integral, I would just say, do a path integral over only coordinate space trajectories from here to here of e to the I action. And that would be it. This factor, you might say, well, that's not the right answer because it's actually off by this factor. Is it important? Well, we don't know yet. I'll just tell you where it's going. It won't be important. Why? Why? Because the reason that I secretly said I really want potentials which are explicitly time dependent, even though, as you see, I just didn't want to keep writing it out with the time dependence. The reason I wanted the time dependence there is so I could introduce source terms when we go to field theory. And the thing that we care about, the only thing we care about, is calculating this. And the only dependence we care about is dependence on the source. So we are going to see that when we generalize all of this, the source term is going to be sitting in the potential. This will not have any source dependence in it. So if I throw away something which is an overall source independent factor, then at least all the functional dependence on the source is faithfully maintained. Okay, so that's where we're headed. And so indeed, this is the piece that we need. Okay, so we'll take that over next time. But right now, I'm happy to just stop with this. But do note that the momentum integral is completely factorized from the position space integral. And we'll do the momentum integral. It's only a Gaussian, so we'll do it.